In this unit, we are going to learn a variety of techniques to integrate functions. Thus far, the only sophisticated method that you know is substitution. Substitution works because what you are doing when you perform a substitution is basically undoing the chain rule. Today, we're going to learn a technique called integration by parts, which undoes the product rule. So we have this integration by parts formula that tells us that the integral of u dv is uv minus v du. Now, roughly speaking, you can think about u as an original function and dv as being the derivative of some other function. And this formula allows us to manipulate the integrand on the left into the thing on the right. So let's sort of show you where that comes from to start. So, as I said, this comes from the product rule, so the first thing you have to do is remember what the product rule says. So the product rule says that the derivative of f of x times g of x is equal to f of x times g prime. So just differentiate g prime. Differentiate g, and then add g of x times f prime of x. Now what we're going to do is take this equation for the product rule and we're going to integrate both sides. In the same step, I'm going to flip-flop what's on the left and what's on the right. So we have that the antiderivative of f of x g prime of x plus g of x f prime of x. So antiderivative of that expression has to equal the antiderivative of the derivative of f of x times g of x. Now this right side is easy to deal with if you anti-differentiate the derivative of f of x g of x. So first you differentiate the function, then you take the antiderivative of the function. That is just going to give you back f of x times g of x. On the left, we're going to break this into two integrals. We have the integral of f of x g prime of x dx plus the antiderivative of g of x f prime of x dx. And now we're going to isolate this integral, so we're going to move the second integral onto the right-hand side of our equal sign by taking it away. So we have the antiderivative of f of x times g prime of x dx is equal to f of x times g of x minus the integral of g of x times f prime of x dx. And to make it look just like the formula that you have above, we let u equal f of x. So the derivative of u du is f prime of x dx, and similarly v is equal to g of x, and dv is g prime of x dx. And making those substitutions just for the notation, we have that the integral of u dv is equal to uv minus the integral of v du. And this might not seem immediately useful at first, but this allows you to take your integrand and manipulate it into something else that is hopefully easier to evaluate. Now, the most common instance where you see this is when you have a product of two functions. So the formula says that the antiderivative of, that the antiderivative of u dv is equal to uv minus the antiderivative of v du. So you take your integral and identify one function to be u and one function to be dv. So usually you choose u to be the function who sort of goes away as you take repeated derivatives. So we're going to let u equal x. Then the derivative of u is dx. So we've let u equal that part of the integrand. And dv is going to be the rest, cosine of 5x dx. Now to translate this integral into the one we're going to get for the formula, we have to find the function v. We have dv, or the derivative of v. So to find v, we have to antidifferentiate cosine of 5x. And the antiderivative of cosine is sine. And the way you compensate for that 5 inside with the x is you have a coefficient of 1/5 with the reverse chain rule. So that tells us what u and v are. And so now let's see what happens to us when we manipulate this integrand. So this integrand is equivalent to uv. So x times 1/5 sine of 5x minus the integral of v du. So minus 1/5 sine of 5x. And then du is just dx. So we have 1/5 x sine of 5x minus 1/5 times the integrand of sine of 5x. And now this integrand that we have, the integral of sine of 5x, something that we can do very easily. It's just a basic sort of reverse chain rule type substitution. And we have to do the substitution if you can compute that in your head. So our final answer is 1/5 x sine of 5x minus 1/5 times the antiderivative of sine of 5x is negative 1/5 cosine of 5x plus c. So your final answer is 1/5 x sine of 5x plus 1/25 cosine of 5x plus c. And if you'd like to, you can check your answer by differentiation. If you differentiate this answer, you should get back x cosine of 5x. If you choose to do that and check your work, don't forget to use the product and chain rules. Now, integration is not as straightforward as differentiation. There are techniques you can apply in general situations in which they work. Sometimes you have to apply them more than once. And this is an example of where we'll have to do integration by parts twice to find the antiderivative. So in our first round, like I said in the previous example, we start by choosing u to be the function who sort of goes away as you repeatedly differentiate it. So we're going to let u equal x squared, and we're going to let dv equal e to the x dx. So if u is x squared, du is 2x dx, and if dv is e to the x dx, then v is e to the x. So now the antiderivative, so we have the integral of x squared e to the x will be equal to uv minus the integral of v du. So we'll have x squared e to the x minus the antiderivative of, so v du will be 2x e to the x dx. And that 2 can be factored out of the integrand. I think it's easiest to do so, so let's do that. x squared e to the x minus 2 integral x e to the x. All right, so you don't have a great easy way to antidifferentiate x e to the x. But you could imagine that, say doing this first iteration of integration by parts took that x squared that was inside the integrand and reduced it to an x. If you, so the derivative of x squared, that's where that 2x comes from. If you do it again, that x will reduce to its derivative, which is just 1, and then you're just going to have the e to the x left, and you can integrate that. So we're going to repeat the process, so choose, and we're going to repeat it with just this integral, and we're just going to carry along our other terms for the ride. So let u equal x, and let dv equal e to the x dx. So now du is just dx, or 1 dx. V, the antiderivative of e to the x, is e to the x. All right, so we have x squared e to the x just hanging out for now, minus 2 times uv, and here's the important thing, since this integral of x e to the x dx expands into 2 terms, you must put parentheses around those terms. So uv x e to the x minus the integral of v du, so minus the integral of e to the x dx. I think it's easiest at this step to distribute that negative 2 through. Don't forget to send the negative along with it. So you have x squared e to the x minus 2x e to the x plus 2 integrals of e to the x dx. And now the integrand that you have is reduced to something that you can actually do. The antiderivative of e to the x is just e to the x. So you're home free. And your antiderivative is x squared e to the x minus 2x e to the x plus 2 e to the x. And at this stage, don't forget plus c. If you want to, the greatest common factor from those first 3 terms is e to the x, and you can factor that out. So e to the x times x squared minus 2x plus 2, and then plus some constant c. That's not required, it's just, for example, Wolfram Alpha gave me that answer. It's good to know that it's equivalent. Now notice that the power was, on the x was x squared. The integration by parts process went through 2 iterations. And I think you can probably convince yourself that if that were an x cubed, the integration by parts process would have gone through 3 iterations. And in that case, I think you're going to want on your homework, it is really important to take care of this distribution probably right away and just keep really good track of your negative signs. I wouldn't be so mean as to give you the integral of x to the 4th e to the x. You don't want to do it, and I'm not particularly interested in grading it. All right, here is our first example of an integral where we do not let the u equal the y or x to the power. We're actually forced to choose the other way. And the reason is that if you were to let ln of y be dv, you would have to antidifferentiate ln of y, and you don't know the antiderivative of ln of y. You know the derivative of ln of y. So you're forced to let u equal ln of y, in which case du is 1 over y dy, and then you'll let dv equal the rest of the stuff, y to the 3rd dy, and not so hard, v is 1/4 y to the 4th. And you're really hoping that that works. But as is the case with much integration, you just need to try something and see if it works, and if it doesn't, ask for help and try something different. So remember, the formula is uv minus the integral of v du And the other difference with this example is that we have a definite integral, which will introduce a little bit of notational differences. So uv is 1/4 y to the 4th ln of y minus the integral of v du. So that will be 1/4 y to the 4th times 1 over y dy. And I left the bounds off on purpose just because I like to show you how to put them in correctly. So this first term no longer has an integral sign, so that you're going to evaluate right away, as in draw that straight bar and tell me you're going to plug in e and then 1, just like that. In the second part, you still have an integral, so just keep the same bounds, 1 to e. All right, now evaluating the first term, we'll have 1/4 e to the 4th ln of e minus 1/4 times 1 times ln of 1. And then minus 1/4 times the integral from 1 to e. And notice how nicely that y to the 4th times 1 over I reduces to y to the 3rd. As there are no hard and fast rules for how to pick u and dv, you just have to try a whole bunch of problems to get the patterns down. So this becomes, remember, ln of e is 1 and ln of 1 is 0, so we have 1/4 e to the 4th minus 1/4 times 1/4 y to the 4th evaluated from 1 to e, and that's 1/4 e to the 4th minus 1/16 y to the 4th evaluated from 1 to e. And that negative sign's a bit tricky here, so just be careful. We'll have 1/4 e to the 4th minus 1/16 e to the 4th minus 1/16. Notice how when I plug in e and 1 into my 1/16 y to the 4th, I put parentheses around those two terms. That negative will distribute. And we have 1/4 e to the 4th minus 1/16 e to the 4th plus 1/16. And you can combine like terms. The 1/4 e to the 4th and 1/16 e to the 4th can combine. So get a common denominator that is 4/16 e to the 4th minus 1/16 e to the 4th plus 1/16, which equals 3/16 e to the 4th plus 1/16. So that's one great answer. Or you could factor out the 1/16 and write it as 1/16 times 3e to the 4th plus 1. So be careful with your notation when you have a definite integral, and then also observe that it isn't the case that you always let u equal y to the 3rd. All right, now I said that we don't know a formula for the antiderivative of ln of x, and this integration by parts technique gives us a way to derive one. And once again, we can't antidifferentiate ln of x. We're forced to let u equal ln of x. And you feel a little bit like, well, there's nothing else left to choose to be the dv, but don't forget about that dx. dv is just equal to dx, or you can think 1 dx. So in this case, du is 1 over x dx, and v is the antiderivative of 1, which is x. And maybe you're skeptical that this is going to work, but it'll be very similar to the last example. So remember that the formula is uv minus the integral of v du. So x ln of x minus the integral of x times 1 over x dx. And huzzah, x times 1 over x is 1. So we have x ln of x minus the integral of 1. And whoa, you can do that. You can do lots of other things too, but at least that. X ln of x minus x plus c. And don't forget that you can always check your answers. I mean, occasionally the checking is quite complicated. That's why I don't like always make you do it. But in this case, let's do it. So we're going to check that this actually is the antiderivative of ln of x. And we're going to do that by taking the derivative of our result. So derivative of x, ln x minus x plus c. And as long as we differentiate this correctly, we should get back ln of x if we did this actually is an antiderivative of ln of x. So to differentiate x ln x, you must use the product rule. So I'm just going to differentiate the x first. That gives me 1. The ln x doesn't get differentiated. And now we have x plus x times 1 over x. And then the derivative of x is 1, so minus 1 plus 0. And that is ln of x. X times 1 over x is 1, so ln of x plus 1 minus 1, which is just ln of x. Bam. So look, the antiderivative of ln of x is x ln x minus x. And that is a formula that we can use to anti-differentiate ln of x. Notice it's not 1 over x. That's the derivative, not the antiderivative. Just in case that wasn't clear. Now let's use our brand new fancy formula to find the antiderivative of ln of 3x plus 1. I think it's best here to do a substitution. So think back to calculus 1, which I know was a while ago, but anyhow, substitute for the 3x plus 1. U is 3x plus 1. Du is 3 dx. So a third du equals dx. So this becomes 1/3 antiderivative of ln of u du. And now we know that the antiderivative of ln of u is u ln of u minus u plus c. What I wrote is technically a little bit wrong because that 1/3 must distribute to all terms, so either distribute it or put parentheses. And now we just reinsert what u was. So 1/3 times 3x plus 1, don't forget your parentheses there either, ln of 3x plus 1, once again parentheses, minus the quantity, 3x plus 1, and don't forget your parentheses. I think if I say that 10 times you're going to remember them, don't forget your parentheses. Now the last thing you can do is you can take out the greatest common factor. This 3x plus 1 and that 3x plus 1 can be factored out. And we have 1/3 times 3x plus 1 times ln of 3x plus 1 minus 1 plus c. Now the method used to find the antiderivative of ln x can also be used to find the antiderivative of inverse trigonometric functions, such as inverse tangent. Also works for inverse sine and inverse cosine. The resulting integral that you get when you do the iteration of integration by parts is a little bit more complicated in this case, and you have to use both the integration by parts technique and the substitution technique to get the antiderivative of this function. So once again, we're forced to let u equal tan inverse of 2x. And I made it a little bit complicated on purpose because I wanted to make sure you can still do calculus 1. The derivative of inverse tangent of 2x is 1 over 1 plus 2x, the quantity squared. And then don't forget the chain rule because there was a 2x inside your inverse tan. You've got to multiply by 2 dx. If you remember that, high five. And then dv will equal dx and v will equal x. So there's our basic setup. And I made this one so much fun because I also put bounds on it, so yippee! So uv, so we have x inverse tangent of 2x, and that will be evaluated from 0 to 1/2, minus the integral from 0 to 1/2 of v du. And just think ahead a little bit. You multiply v times du, that x and that 2 end up in the numerator. I'm going to actually pull the 2 out, and I'll have x over 1 plus the quantity of 2x squared makes 4x squared dx. So lovely, here we go. So first let's do the whole plug-in 1/2 plug-in 0 bit. So we have 1/2 tan inverse of, well, 2 times 1/2 is 1, minus 0, because any case, whatever inverse tangent of 0 is, you have 0 times it. So in this case, you escaped without having to find inverse tangent of 0, but it's 0 just in case you want to know. And then minus 2 times, I'm going to pause a sec. So here you have to be able to recognize that you now know 2 techniques, one of which is integration by parts and one of which is substitution. You can't forget about substitution. You have to use it sometimes. And this is a case in which you must do so. And it takes lots of practice to figure out what to substitute for. So in this case, the best substitution is to let u equal your entire denominator. And actually, no, we can't use u because it's bad mathematical form to reuse variable names. So I've already used u. I'm going to use a different letter. I'm going to use w. So w is going to be 1 plus 4x squared. And note we also have a definite integral, so we're going to have to change our bounds. So dw is then 8x dx, and we just have x dx, so we'll divide by 8, 1/8 dw equals x dx. And the bounds, it's not written in the integral, but that really means you start at x equals 0 and you go to x equals 1/2. So you have to figure out what are the corresponding w values at those points, and you use your substitution. So if x equals 0, this implies, using this substitution, that w will equal 1 plus 4 times 0 squared, which will be 1. And if x is 1/2, using the substitution, we get that w is 1 plus 4 times 1/2 squared. Since 1/2 squared is a quarter, and 4 times 1/4 is 1, 1 plus 1 gives us the w is 2 at that case. So the bounds change to 1 to 2, 1 over w dw, and don't forget about the whole over 8. I'm going to put that right here. Okay, great. Now back to our first thing, making you find inverse tangent of 1. Yes, you have to know the values of certain inverse trig functions. There are not very many. It's only going to be simple ones. So you have to think to yourself, when does tangent equal 1? Specifically between negative pi halves and pi halves, and think, well, if tangent is 1, sine and cosine must be equal. That happens at pi quarters. That's the easiest one I can give you. You're supposed to know that. There are others that you should be able to figure out if you, say, have some time in a unit circle, but inverse tangent of 1 and negative 1 and 0 are things you really should know. So minus 1/4, the antiderivative of 1 over w is ln of absolute value w, evaluated from 1 to 2. Because you changed your bounds, there's no reason to go back to x's. You said the area underneath x over 1 plus 4x squared from 0 to 1/2 is the same as the area from 1 to 2, 1 over w. So no need to go back. So this will give us 1/2 of 1/4 is 1/8, so pi eighths minus 1/4 times ln of 2 minus ln of 1. Note the parentheses. In this case, they're not super important because ln of 1 happens to be 0. So your final answer is pi eighths minus 1/4 ln of 2. Now this next one looks as if it might be kind of icky, but you just have to try something. So probably going to have to let u equal that complicated bit, because there's no way I can take an antiderivative of it. So you're forced to let that happen and just kind of hope it all works out for the best. So u is ln of x, the quantity squared. And to take its derivative, you have to remember the chain rule from calculus 1, so it becomes 2 ln of x to the first, I'm not going to write that, times 1 over x dx. So, okay, I took the derivative correctly, good job. dv will equal x squared dx, giving us that v is 1/3 x cubed. So remember, the formula is uv minus integral of v du. Okay, so we have uv, I'm just going to put the v first, 1/3 x cubed, ln of x, the quantity squared. Don't leave off those parentheses or it looks like x is squared, not the entire ln expression, minus v du, so minus the integral of 1/3 x cubed times 2 ln of x times 1 over x dx. I didn't simplify that on purpose just so you could see what goes where, but if you can do this on your own and simplify quickly, that's not a problem. So we have 1/3 x cubed ln of x, the quantity squared, minus, let's think, the coefficient that we have there is 2/3, that can be factored out. The x cubed times 1 over x just makes x squared, and the ln of x is still hanging about. There we go. Now it appears as if this is something we're going to have to sort of repeat the integration by parts process. This is very similar to a previous example that we had where we had x, I think it was y cubed times ln of y. Almost the exact same process. So let u equal ln of x, du will equal 1 over x dx, so back to some simple things. If you let dv be the remainder of the stuff, so dv will be x squared dx, and v will equal 1/3 x cubed. All right, so we have 1/3 x cubed ln of x squared minus 2/3, don't forget your parentheses, uv, so 1/3 x cubed ln of x minus v du, or minus the integral of v du, so minus 1/3 x cubed times 1 over x dx. Be very careful with those parentheses, and I'm going to distribute the negative 2/3 through and also simplify that integrand a bit. So we have, we're almost done, 1/3 x cubed ln of x squared minus 2/9 x cubed ln of x, and then plus 2/9 times the integral of x squared dx. And after 2 iterations of integration by parts, we've reduced this down to something that we can do. The antiderivative of x squared is x cubed, well, 1/3 x cubed, excuse me. So we have our antiderivative is 1/3 x cubed times ln of x squared minus 2/9 x cubed times ln of x. And we're going to have 2/9 times 1/3, which makes 2/27 x cubed. And then don't forget your plus c. So So that wasn't so bad. Checking this would be really, really tedious and probably quite painful, so lots of room for error, so let's not do that. But the point is just give something a try and see if it works. Now, there is an instance in which some trickery happens. So this function, you're like, well, geez, you told us that you let u equal the thing that goes away as you differentiate, and neither of these functions, quote unquote, go away as you take derivatives. E to the 2x, it just keeps differentiating to multiples of itself, and sine of x just kind of flip-flops between positive and negative sine and cosine. So, blah, what do you do? So there is this trick that's sometimes called around the world, just to give what we're doing a name. And it's a little bit clever. So it involves doing 2 iterations of integration by parts and then one clever step, which I'll point out when we get to it. Now you have a choice here. I'm going to put the good choice first and the bad choice next. So you can let u equal e to the 2x, and you can let dv equal sine of x dx, or you can let u equal sine x, and you can let dv equal e to the 2x dx. In the instance of the second choice, you're going to have v is 1/2 e to the 2x, where the first choice you're going to have that du is 2 e to the 2x dx. Now, in my experience, working with whole numbers is easier than working with fractions. So in this case, it's probably better to let u equal e to the 2x. Had that 2x been inside the sign and not inside the e, you would have let the u equal the thing with the sign. You just had to choose. And once you've made your choice, you have to keep that choice throughout the remainder of your work. So the second method isn't wrong, it's just that the first method I think is a little bit better. So let's erase that. I'm gonna not do it that way. And continue with our substitution. If dv is sine x, the antiderivative of sine is negative cosine of x. Okay, so there's round one. We have that the integral of e to the 2x sine x dx is equal to uv. So minus e to the 2x cosine x minus v du. So minus the integral of negative 2 e to the 2x cosine x dx. I'm going to factor out that 2, take out the double negative, and I have negative e to the 2x cosine of x plus twice. That's a bad plus, let me fix that. Plus twice the integral of e to the 2x cosine x dx. And you're on a roll, so you're like, well, I can integrate by parts. Let me try it again. So pick the same sort of substitution order on your next substitution, or your next integration by parts iteration. Let u equal e to the 2x again. Du is 2 e to the 2x dx. dv, we're going to let that be cosine of x. And v is then sine x. So we have our original integrand is equal to negative e to the 2x cosine x plus 2 times the quantity e to the 2x sine x, so uv, minus v du. I'm just going to take that 2 out right away. So minus 2 integral e to the 2x sine x dx. Now don't operate blindly. Notice that the thing inside your integrand is back to what it was in the beginning. Now that's key. That's when you sort of stop. So first let's distribute the 2. So we have negative e to the 2x cosine of x plus 2 e to the 2x sine x minus 4 integral e to the 2x sine x dx. And now here's the clever step. This whole thing over here is equal to this, as in specifically one of those integrals. We are going to add this. We're going to add 4 integrals of e to the 2x sine x dx to both sides. And that is going to make this into 5 integrals of e to the 2x sine x dx. That's equal to negative e to the 2x cosine x plus 2 e to the 2x sine x. And now's a good time to put in that whole plus c business. Whoa, crazy. And now you want to find the integral of e to the 2x sine x, not 5 of them, so you just divide by 5. And the integral of e to the 2x sine x dx is equal to negative 1/5 e to the 2x cosine of x plus 2/5 e to the 2x sine x. And c divided by 5 is just another different constant, so just say plus c again. So there you go. That's called around the world. It's a tricky trick, and you use it when you have a combination of, say, like e and sine. It also can be used with combinations of sine and cosine, but that's a little bit more challenging. Usually you can recognize it by recognizing even e and a sine. Now here's an example where you do a substitution, and once you do that, it reduces to something where you have to use integration by parts to keep going. And so knowing that the integration by parts formula involves u's and v's, I'm not going to use u, I'm going to use w. When I was in Calculus 1, actually, my textbook purposefully only used w's for substitutions. So we're going to let w equal the thing inside the cosine. W equals x squared. And then dw is 2x dx. So 1/2 dw equals x dx. These are a little bit tricky, but how you start is you take that x cubed, and it works because we have x cubed, and you break this into the integral of x squared times x cosine of x squared dx. And you said that x squared was w, so this x squared is a w. This x dx, that's your 1/2 dw's, put the 1/2 out in front, put the dw out in the end. And then you have cosine of w. And it's a basic integration by parts problem, probably the simplest one I can give you. So you'll let u equal w, du is dw. You'll let dv equal cosine of w dw, and then v is equal to sine of w. So there we go. So substitution and then integration by parts. As opposed to the other examples where we had, where first it was integration by parts and then substitution. So we have 1/2 times uv, w, sine w, sine, not sim, minus v du, so minus the integral of sine w dw. All right, and that's 1/2 w sine of w. Whew, the antiderivative of sine is negative cosine. So simplify the double negative and plug back in your substitution. So your final answer is 1/2 x squared sine of x squared plus cosine of x squared, and then plus c. So that one substitution wasn't ridiculously tricky. Our final example substitution is a bit tricky. So just like the previous example, we let w equal the thing inside of the sine function. We're going to do the same thing here. So w will equal root x. I know it seems like it's going to lead you nowhere, but just give it a try. And then dw will be 1/2 x to the -1/2 dx, or dw equals 1/2 root x dx. And the tricky thing now is you multiply that 2 root x over with the dw. So you got 2 root x dw equals dx. And root x is w. So you got 2w dw equals dx. It's a little bit strange, but that's how it came up. So this becomes sine of w, and dx is replaced by 2w dw. So that becomes 2 integral of w sine w dw. And that's effectively the exact same integral that we had in the previous example after we did our substitution, so it's a pretty basic integration by parts. And these problems, from what I can tell in the homework assignment, are actually sort of spelled out for you as in first do a substitution and then integrate by parts, just to give you a hint as to how to start. The only way to learn what to do is to practice and get some experience. So we're going to let u equal w. du is dw. dv is sine of w dw. And v is negative cosine of w. So we have twice, don't forget parentheses, u, v. So negative w cosine of w. Minus v du, so I'm going to say plus right away because I've got a double negative. So minus the integral of cosine of w dw. All right, so 2 times the quantity negative w, cosine of w. Antiderivative of cosine is sine, so plus sine of w plus c. And insert substitution. 2 negative root x cosine root x plus sine root x plus c. And that is your antiderivative. That is probably as complicated as an integration by parts problem could get, at least thus far, so that's the hardest kind of example you're going to have to know. Good luck on your homework.